All right. Well, Kevin, we've been talking about doing these mini-sodes, if you will, for quite some time. And I know that as the Wolfpack is getting ready to kind of rebrand with a new trimester, one of the things we noticed is that, it's kind of like having to start over with the understanding of some of the basics of CubeSat. So this episode is going to share a little bit about the CubeSat history. Is that right?
Yes. Yes, we're going to look at the origins of the CubeSat form factor and spend a little time introducing it. And then that will lead us to some future episodes where we'll look at some of the more well-known CubeSat missions, some of which are even interplanetary, not just in orbit around the Earth. And we'll look at subsystems and then a few other topics.
Great. So for those of us or those of you listeners who also follow our YouTube channel, you'll be able to see the slide deck that Kevin will be showing today there as well. But for those of you who are podcast listeners, me being here, I'm hoping to be able to help guide you in the process so that you don't have to go there unless you're looking to do that later for more edification. So as we get into it, I wanted to go ahead and ask you a little bit, remind us why CubeSats are so essential.
Well, CubeSats are an important learning tool. So if you are an educator or a student, or you're interested in aerospace or engineering or astrobiology or physics, electrical engineering, almost any STEM topic is encompassed in designing, building, testing, or flying a CubeSat and then operating it while it's on orbit.
Who normally does that?
Well, small satellites for a long time were the domain of graduate students, companies, NASA, the Department of Defense, entities like that.
And yet you do it with middle school students?
Yes, there are a couple of high schools in the country that have very respectable CubeSat programs, and they've launched more than once. And there have been two middle schools which have launched CubeSats, and I happen to be the principal investigator for the first group of middle school CubeSat team.
And then now some of those very students that you worked with are in high school looking to build their own. And so that is something that the Wolfpack does, is help students who are interested in creating these CubeSat proposals, not only to propose them, but to ultimately, as you had pointed out, to build and launch them as well. So why don't we go ahead and get started to learn a little bit more about where they came from and why we use them?
Sure. So the story, I don't want to say the story begins and ends with Bob Twiggs and Jordi Puig-Suari, but these are the creators of this form factor. Now, satellites come in many sizes. You may recall that the Hubble telescope was the size of a school bus, and it had to be launched. It was a requirement that it be launched in something really large like the cargo bay of the space shuttle. Today, we're finding that instead of building a multi-billion-dollar large satellite with a lot of functionality, it is better to build a network of smaller and less expensive satellites, which has a number of advantages. Number one, if you are imaging the Earth, for instance, you get a lot more temporal resolution. You get to see the Earth many more times a day, the more satellites you have in a constellation, if you will. Also, the cost comes down a lot. So whereas the Hubble, something like the Hubble or James Webb, those are multi-billion-dollar, multi-decadal missions. The technology changes so rapidly now, it's better. Many find it advantageous to fly lower cost satellites and have the advantage of upgrading your technology almost persistently as you put up the next small satellite.
Are they still alive?
Oh, absolutely. Dr. Bob Twiggs is the founder. I mean, he really is the genesis of this idea. I've heard him tell this story live, and I've listened to his podcasts, and I've listened to him tell the story through videos, but it's really cool to hear it in person. He said back in the 90s, he had worked with some microsats, right? Think about a college refrigerator size satellite. But every time you try to build a satellite, everybody wants to throw their sensors or their instruments on it. And the missions suffer from something called scope creep, where everyone is trying to add their particular item to the satellite, and It just extends the timelines and makes the budgets go up. And he literally thought, what if I de-scoped and simplified this problem? And what he was doing was training graduate students at Stanford. So Bob Twiggs was at Stanford, and Jordy was nearby at San Luis Obispo at Cal Polytech. And Bob says, what if I got a really small form factor? And he literally went to a store and picked up an empty Beanie Baby box. And he looked and he said, could we fly a satellite this small? And if it was small, there were a couple of advantages. One, people wouldn't be able to add. You would have to really simplify what went into it. But more importantly, as an educator, there was a need for a tool where graduate students, could design, build, test, and fly a satellite in the time that they were in graduate school. So this is around the turn of the millennium. Around 2000, he comes up and he shows up in class with this Beanie Baby box. And what is so fascinating and so interesting to me is one of my friends who teaches at the Naval Academy now, Dr. Jen Kang, he was actually a graduate student in Dr. Twiggs' classes there at Stanford when the CubeSat was invented. So just building a CubeSat, though, isn't enough. And the CubeSat resulted from a number of innovations. One, microelectronics. Think about all of the research, the billions of dollars that went into smartphone technology. So you have the miniaturization of electronics. You also have access to rides. But at first, there was a lot of reluctance because no one wanted to risk their multi-billion-dollar payload on some cheap piece of a student payload. So the true genius of what Jordy and Bob Twiggs did is that not only did they invent the form factor, but they invented a deployer which would ensure that the primary payload would be safe. And the original deployer was called a P-pod. That's Poly-Picosatellite Orbital Deployer, or P-pod. So now you have the satellite, you have the deployer is mounted on the rocket. The launch providers and integrators and those with the primary payloads could feel that their mission was protected. So the CubeSat became what was known as a secondary payload, which meant you were along for the ride for the primary customer.
Are they both still professors right now?
They both retired. And yes, they both retired, but the industry that they spawned has just taken off in an incredible way.
And was Twiggs at University of Florida, and you still have some current Wolfpack students who are working?
No, not Professor Twiggs. I first learned about CubeSats from a professor named Dr. Norm Fitzcoy.
Okay.
And so Fitzcoy, his doctorate, he learned, he was an aerospace engineering PhD student out of Auburn University. He is faculty at UF, and he was one of the early builders of a CubeSat. His CubeSats are SwampSat 1 and SwampSat 2, and he's currently involved with a big project called DebrisSat.
Mm-hmm. Well, that's pretty interesting about how, these folks have made such an amazing contribution to CubeSats are still doing that. Even though, space moves quickly, it seems like it's really just kind of going from what these two started. So that's pretty impressive.
Yes, let's take a minute and talk just a little bit about what exactly is a CubeSat and why is it so novel. So the actual physical size of a CubeSat is a multiple of what we call a U, or unit, 1U. So a 1U CubeSat is basically a cube shape 10 centimeters on a side with a maximum mass of 1.33 kilograms. So if you think about it, it's 2.5 pounds max satellite, and it's a little bit bigger than the box that you would find a softball in. And what is so fantastic, I did a little research and I found a nice website that keeps a nice archive of all the launches. And this is from nanosats.eu. And as of May 31st of 2023, there's been 2,286 nanosatellites launched and 2,105 CubeSats. So you may hear the phrase picosat, CubeSat, and nanosat used sort of interchangeably, but really CubeSat means a spacecraft that is smaller than a microsat. So microsats are on the magnitude of, say, 100 kilograms or 220 pounds. But when you look at a CubeSat, you're looking at multiples of that 1U from, say, 1 to 12U. Very common are 3U CubeSats, and we have sent the Marco CubeSats, for instance, were 2 that we sent past Mars, and they were 6U.
Is that what Wolfpack VIP member Colin is working on?
Colin Quinn is one of our Wolfpack members. He is our lead for our first 3U CubeSat that we hope to send beyond the Earth's magnetic field. And what's interesting is our first 2 CubeSats, the YSat and the CabSat, they were both 1U CubeSats.
Well, what's the benefit of like having a bigger sized one? I would think that's more expensive too.
Oh, yes, the cost. And one reason, as a middle school teacher with a CubeSat team, the 1U, we were able to fund that. So the 3U is going to be much more expensive. But as you ask, when you have a larger CubeSat, what you see is that you can have larger batteries, you can have larger solar arrays to generate more power, more wattage, which means you can carry more scientific instruments. So whatever your mission is, you can be more robust, sometimes with a larger payload.
But it's safe to say no matter what size, you have to have some kind of power source in order to run whatever it is. So in a CubeSat, it sounds like there are components that have to be part of it, no matter how small it is. Power to turn on whatever it is that you're going to test in the payload. Is that right?
Right. So normally we break down a CubeSat or any spacecraft into 2 major systems, right? 2 major parts. So one is the payload. The payload is always the reason that you go to space. So in the case of the YSat, for those of you on the YouTube channel, you can see in the video, the middle image is our 1U YSat, which is a 1U CubeSat, whose mission was to evaluate extremophile bacteria in low Earth orbit. So there you can see a 1U CubeSat. And this CubeSat was mounted in a deployer. So it's a rectangular apparatus that typically has a spring-loaded door and a spring to gently push satellites out as the rocket is ascending into orbit. So that's why we're called secondary payloads, CubeSats are, and they're catching a ride, and basically their orbit becomes mostly wherever the rocket or the spacecraft ejects them.
Well, let's talk about these missions for a second. I mean, why would we care about extremophiles in space? I mean, what can we learn from, what do we care about that here on Earth?
So I find that most interesting, and what I've enjoyed most with the students is letting them ask questions. And there are some really good questions that can only be answered if you fly a mission to space. And so with students, their accessibility to space is greatly enhanced with the CubeSat. And what I think is most important is that we are preparing them for 21st century jobs by giving them some hands-on and real-world experiences.
Well, I know that this is just kind of a mini episode and that you're going to be teaching like a class on this and you're going to be reintroducing the history of this to your Wolfpack members. But if you had that one with the first mission, you then had the CapSat with Sammer. So those applications about, if I believe the mission was to like test a capacitor as opposed to batteries in space, were there ramifications that we could use here on Earth for that as well?
Well, I think all good research that's done in space, there is ultimately some spin-offs that benefit us here on Earth. Lithium, we do need a substitute for lithium batteries, or we need to improve the process. It's very, environmentally, it's not, our best option. We need to find better ways to use renewable energy sources on Earth that don't strip a lot of resources out of the ground or create extra pollution, et cetera.
Well, with that one, how long did it take Sammer to come up with that idea and then to get it completed?
Sammer was a 7th grader when he came to me with the idea for a mission, because I always allow the students to pitch ideas, and then the best ideas rise to the top. He was selected, I believe, in the spring of his 8th grade, but it wasn't until the summer of his 10th grade that the CubeSat flew on a Falcon 9 on a crew resupply mission, CRS, which is a Dragon capsule full of supplies and water and clothes and whatnot, experiments up to the ISS. His mission, that satellite was then loaded onto the Japanese ports, the Kibo, and in September, it was pushed out into space. Our first satellite, on the other hand, as for those of you looking at the images, you can see it lifted off on a Falcon 9 from Vandenberg, which is now called Space Force Base, but it was still Air Force Base on December 3rd, 2018.
And then I guess Theo is the one that's about to be launched. That's being launched differently, right? So
That's
that's
right.
a different kind of payload too, right?
So Theo Uyang is one of our 11th graders who started in the 5th grade with us. His mission also was, he was turned down by NASA twice, but one of the Wolfpack members created a philanthropy and raised the money to not only build the hardware, but also pay for the launch cost. So FlipSat is unique in that it will not be a free-flying satellite on its own. It is a component of a device called the Troop hardware made by Near Space Launch. So Theo's mission, which is looking at bit flips in low Earth orbit, particularly if you think about the South Atlantic anomaly, it's a place where the Earth's magnetic field is a little weaker and dips in. And we often, we find that sometimes electronic spacecraft, they're susceptible to the ionizing radiation up in space. And that's the basis of his experiment. But his experiment is flying as part of a larger device.
Well, I know that this is just supposed to be an overview. So before we shut this episode down or this mini-sode down, is there anything else that you think that a person just kind of who might want to get excited about CubeSat should know?
I think the most important thing you should take away from this about CubeSats is that this is not only real world and very exciting engineering, but this is a chance for you at a very young age to put your hands on something that not only is going to prepare you for work in the future, but also you get to send, you'll be working on something that will go to space. So I feel like those are, the CubeSats are a very exciting tool.
Right. So what's good to know too, for those who are interested in learning more, is that you plan on maybe having some classes that are going to be available. So how could people who are listening who might be interested in actually taking some of these online courses reach you? Can they reach you via email to find out more?
Yes, absolutely. So if you go to our website, aerospacehigh.org, aerospacehigh.org, you'll find information about our upcoming space clubs and the Wolfpack.
Right. But I mean, if they wanted to get like your classes on, that you're going to be doing eventually with these, they can reach out to you at email KSIMMONS@bluecubesat.com. That's BLUECUBESAT.com. So KSimmons@bluecubesat.com. And of course, we'll be talking a little bit more about those classes should they be offered in the near future. Yes.
Yes.
All right. Well, that's good. We look forward to the next mini-sode. What's coming next for us in the pike of things?
I think our next episode will be looking at some well-known CubeSat missions that have already flown.
Okay.
We'll talk a little bit about the CapSat, but also Marco, which are 2 CubeSats that we sent past Mars, and some interplanetary and some very interesting missions here around the Earth.
That would really help people knowing about some of the ones that were important like that to come up with their own ideas, I can imagine.
Absolutely.
All right. Well, we look forward to the next mini-sode.
Thank you.
Thanks for joining. And make sure you join us for the next mini-sode when we say, let's go to space.